So my name is Ramez Naam. I'm a former computer scientist from Seattle, Washington. Spent some time at Microsoft. Finishing up my second book right now, which is on the future of the planet and human civilization. Quite a while ago, Dickens wrote these words. The beginning of A Tale of Two Cities was the best of times, it was the worst of times. It was the age of wisdom, it was the age of foolishness, the spring of hope, the winter of despair. We had everything before us, we had nothing before us. And that sort of sums up the opposing views of our future right now. Certainly there's a lot of very legitimate concern about the future of the environment, about the future of things like our energy supplies and peak oil. You hear about the future of rare earth minerals that are in your cell phones and your earbuds and everything else. And at the same time, there are a lot of techno-optimists who talk about the singularity in Ray Kurzweil's case, or just other ways that technology will address future problems or make us tremendously wealthier. So what is it that's going on between these two things, and where does reality lie? Well, my view is this. It's hard to deny that we really do have unprecedentedly high prosperity today. We really are in the richest, wealthiest time ever on this planet. But we also have, and we have even greater opportunities for the future. But we also have the largest risks we've ever faced. As a planet, all of our eggs are truly in one basket right now. We've faced a lot of smaller scale risks in the past, but aside from nuclear war, which was the first truly huge global risk, we're maybe facing the biggest and largest scale risks ever. Now, we have the ability, or at least a possibility, of prospering like never before, with less negative impact on the planet. But just because the possibility exists doesn't mean that we're actually going to get there. Possible does not mean assured. So in my view, important changes are needed, if only to maximize our odds of good things happening rather than bad things. So let's talk about these things. Best of times. So we live this week, they say, the 7 billionth person was born on planet Earth. And fundamentally, if you ignore some of the negative impacts of population, that's a good thing. There's more people alive, thinking more thoughts, having more experiences. For me, the best metric there is of human health and well-being around the planet as a whole is life expectancy, because that correlates heavily with absence of disease, freedom from violence, adequate nutrition, having a safe place, and so on. And that has soared. It now stands at 68 years around the planet, whereas 150 years ago was about 25 years. And these lines here, the line at the top is the more developed nations, the G20, the US, Canada, Europe, Japan. The line at the bottom is the less developed regions. And what you can see if you squint at this graph is the lines are converging. We're having larger gains happen in the poor world than in the rich world, though both are going up. So that's fundamentally a great thing. We have today the lowest level of poverty ever on this planet. This is using one poverty measure, which is inflation-adjusted, $1 a day level. And that has plunged from being more than a quarter of humanity in 1970 to being about 6% today. And if you look at any other measure, if you look at the $2 a day measure, the $1,000 a year measure, all of them have plunged similarly. And a lot of this is because of the rise in prosperity of Asia, in particular, China and India, but the rest of the world overall. In almost every country you look at, with a few exceptions, poverty is on the decline. While population has grown exponentially, our food supply has grown faster. So we actually have more calories available per human being alive in the food system than ever before. Fewer people are malnourished than at any time in the history of the planet, with a possible exception of a couple years ago. So up until 2007, 2008, this was a great downward slope that cut the fraction of people who are hungry in the world about in half over the span of 40 years. It jumped up a little bit, unfortunately, in the last couple of years with the food price spikes of 2008. And we'll talk about that a little bit. It's come down again a little bit, but the progress kind of stalled out a little bit, and we'll see what's going to happen with that. More people have access to electricity than ever before. Only a quarter of people in the developing world had access to electricity in 1970, and now it's closer to 3/4 than it is to 1/4. And that's a fundamental enabler. It means little things like being able to have light at night so you can read and study. You can't have a working educational system, it turns out, without light in the home at night. And that's one of the prime enablers. Speaking of education, so these different colored bars are different years, and the height is how many the average years of education per student in various places around the world. And so you see, of course, that the very rich places like CU, SA&Z, Canada, the United States, and Australia, New Zealand have the highest average educational levels of 13 years per student. But even in the poorest parts of the world, Sub-Saharan Africa, while it's only up to 4 years now, that's up from 1/4 of a year that it was the average there not so long ago. So there's huge room to continue to increase these things. I'm not saying that Sub-Saharan Africa is a great place to live right now, or most of India for that matter, but all these places seem to be getting largely better. Literacy rates, these are different parts of the world, and all of them up and to the right. Literacy is rising, and that's kind of a fundamental enabler of human progress. The UN has something they call the HDI, the Human Development Index, and what you see is, except for a few countries, mostly war-torn countries, the world as a whole moves up and to the right. You can't see this super clearly, but each of these lines is another country, and they're color-coded here. The blue are kind of Europe and America. The yellow that has the sharpest slope are countries in Asia, primarily. Getting past that. Greater equality. So everybody here has been following Occupy Wall Street, right? Everyone has heard the story of how in the United States income inequality has been on the rise, that the spread, the gain in income of the top 1% is outpacing the gain in income of the median, let's say, in America. Well, on a global basis, that's not true. The big story about equality globally is that the poor are rising in wealth faster than the rich. So this is the 1970 distribution of income. So that's this lump right there, the highest purple peak, was the median income in 1970. And if we advance it 36 years, you see that purple hump moved to the right substantially. Whereas, I'm going to go back in time again, if you look at kind of the down slope on the right, is the very richest in the world, this area over here, and it moves far less than the big lump that is the mass of humanity in this time. We can see this in the global Gini index, which is a measure of how much the wealth inequality is, which has dropped by about 10% on a global basis in this time. And again, that is more than anything else a story of China, but it's not just China. It's South Korea, it's Vietnam, it's Thailand, it's large chunks of India, and increasingly it's even parts of Sub-Saharan Africa that are rising in wealth. Okay, so times are great, yay us. Okay? We really do live in the richest and healthiest and happiest period the world has ever seen. We have some problems. So about a decade ago, geologists coined this term, the Anthropocene, as the name for the next geological age. The geological age dominated by human influence, hence the anthropo in there. And you can argue when that began. Maybe it began 150 years ago, maybe it began 10,000 years ago when humanity started farming. But now we are in this place where the future of the planet really is heavily determined by our behavior and not just by some cosmic cycles outside of that. So the planet really is in our hands. I take it everyone here has heard of global warming, or climate change, as we call it now. So this is the amount of temperature change that has happened in various parts of the world since pre-industrial times, over about 150 years. And you can see almost all the world has gotten warmer. It's in the yellows, the browns, the reds. This is a temperature plot of the last 150 years or so, and you see that it goes up and to the right. And these the red line, purple, orange, yellow, are the slopes of this curve, sort of the trend line over different periods. So the red line is the trend line over 150 years, and the yellow line is the trend line over 25 years. And what do you notice? Well, the yellow line has a much higher slope, right? So not only is the planet is warming faster and faster as time goes by. And actually, this is not exactly a revelation. The first fellow who predicted this was a Swedish fellow, Ramez Naam, who looked at carbon dioxide and knew that carbon dioxide trapped heat, and said in 1896, well, if this happens, then industry is pumping out, there was a little bit of industry back then, industry is pumping out CO2, the planet will warm. He thought this was a great thing because he lived in a very cold, dark place. And so he thought, well, there'll be more agriculture where I live and so on. And he's right, there are actually some positive impacts of this. Now, Svenius thought that this would take 5,000 years for humanity to increase temperatures enough for it to be noticeable because he saw carbon emissions as being flat from industry. But instead, they've risen exponentially, and that's led to temperature rising faster and faster. All right, so this is a record of temperature and carbon dioxide levels in the atmosphere over the last 500,000 years. This is taken from an Antarctic ice core. They drill incredibly deep cores in Antarctic ice and extract them. And by looking at the gas bubbles formed in the ice, they can pick out what was the temperature back then, and they can look at how much carbon dioxide was there in the atmosphere back then. And what you see is that these things agree more than we'd like. And right now, the blue line, CO2, has ventured into territory that's not been charted in the last several million years, actually. Definitely not been charted anytime in the past on this graph of 500,000 years or so. And so looking at this, one might guess that that orange line, which is temperature, is also going to go up and up and up. So that's not necessarily a great thing for us here. And in fact, it's been at least 5 million years since we had this much CO2 in the atmosphere. And when we had that much CO2 in the atmosphere last, there was no ice cap in the north, and there was no ice in Antarctica, and sea levels were about 200 feet higher. Now, I'm not saying that's going to happen anytime soon. Even with a very hot planet, it takes a long time to melt that much ice, and potentially that's centuries. But we're heading into a situation that was last repeated when our species didn't exist. From a human perspective, we voided the warranty on the atmosphere. Humans, and not even proto-humans, have ever encountered a climate like this. So this is a long chart that shows a lot of impacts. The impact that worries me most is extreme weather and food. People talk a lot about rising sea levels. Those are a challenge, but they're a challenge that's still out in the future. But I want to tell you that climate change is happening right now, and we're seeing some of it. So how many of you saw on the news, there were a lot of fires in Texas this last summer? Anybody notice that in the news? They were talking about it. Well, this was the longest recorded drought in Texas history in about 150 years of record keeping. And a number of Texas cities, Houston, Austin, set record high temperatures that they had never seen before in all their record keeping. And so Texas burned. Like these wildfires, I think about 4 million acres burned in Texas. That's more by a healthy margin than burns in the entire United States in a typical year. And that had noticeable effects on a few things. The Texas hay crop basically went away. The Texas wheat crop dropped by 60%. Now, America's rich, Texans are rich enough on a global scale. You don't grow enough wheat in Texas, you can import wheat from someplace else, right? That's not such a big deal. But on a global scale, this sort of thing matters. The atmosphere, as it warms, absorbs more moisture. For every degree Celsius the atmosphere warms, it absorbs about 7% more moisture. So that means a couple of things. It should mean that there's more rainfall, right? But it's not uniform in where that moisture goes. The atmosphere, when it can absorb more moisture, has more moisture demand, they say, which means it can suck all the moisture away from a region very rapidly, and then it can deposit it all in another region very rapidly and dramatically. So while you have Texas in a severe drought, just a year ago, you had the worst ever floods happening in the country of Pakistan. And in fact, the area that was flooded was about twice the area of California was underwater. Okay? An area larger than Germany was underwater in Pakistan. These were floods that no one had ever seen. This is China. This is in Yunnan province. A farmer looking at what were fields. China had in 2009 the worst drought ever recorded there, and then in 2010 they had a worse drought than that. There are wells in Xinjiang that have provided water continuously for 500 years that dried up in 2009. And you can guess what this did to agriculture as well. It wasn't good. Worse than that was the European heat wave of 2003. So Europe has been, well populated. They've had printing presses and so on for a long time. Johannes Gutenberg, you would say, created the printing press in 1540. Well, the summer of 2003 was the hottest summer on record since the printing press was invented. This was unprecedented. 70,000 people died. 3/4 of the Ukrainian wheat crop lost. I think in Switzerland, 10% of the forest burned that year. So these are impacts that global warming is having right now. Then last year, the heat returned to Russia, where over the course of 3 months, 55,000 people died of heat in Moscow alone. 11,000 in Moscow alone, 55,000 total. And again, the Russian wheat crop, it's interesting, you look at newspaper reports a little bit before this happened, they're predicting a bumper wheat crop in Russia, a record high wheat crop. Instead, the wheat crop was down by more than half from the previous year because this weather just decimated it, right? I told you this part already. The thing that worries me most about climate change is that with extreme weather events, it becomes unpredictable, our ability to grow food. And food is the most basic energy supply for humanity. And when food gets scarce, bad things happen. I'll give you a couple interesting stats from history that are not reflected in this presentation right here. So some folks went and did a mining of 1,000 years of Chinese history and 1,000 years of Chinese meteorological history, climate history. They took data from tree rings and from sediments at the bottoms of lakes and said, what was the climate like? And then they correlated that with the rise and fall of empires and with uprisings that happened there. What they found was that when drought hit China, uprisings happened and empires fell. Because when people don't have enough to eat, they get very restless. They're not very happy about this situation. A lot of social change happened in Europe as a result of the Black Death and a great famine in 1315. Those two things led to reduced power of the Catholic Church, among other things. So when conditions are scarce, when resources are scarce, people get into more conflict, okay? So that's extreme weather. Can we blame any of that on climate? I'm just saying these stories, right? Okay, when we look at the data, what we find is that extreme weather events around the world are on the rise. So this data, I've got the whole data set here, but because of potential problems with how records were kept back here, we can just look at 1980 forward, where then we know that this data is really good. Look at the frequency of floods, extreme temperature events, the red here, and droughts, storms, wildfires, all of them on the rise substantially around the world. So when you have more heat in the atmosphere, you have more energy. That energy sucks up more water, it creates higher winds, it moves things around. And it's not a very happy thing for the planet. Okay, so that's what's happening today. Climate change is happening today, and it's increasing the rate at which those extreme weather events are happening. I'm not going to say all of those were due to climate change, but I will say that climate change has increased the number and severity of such events. So some of them, you could say, were due to climate change. But there are worse possibilities than this. And the worst possibilities are rapid feedback loops. Okay? So understand feedback loops. Do you understand when you have feedback that happens with a microphone and a speaker, and you get that out of control whine? That's because a signal is being amplified and fed back and amplified and fed back and amplified until it cranks up kind of beyond where it makes any sense at all. Well, in the climate system, possibilities of this occur. So some of them are positive. For instance, as you get more CO2 in the atmosphere, plants take up CO2. So more CO2 in the atmosphere means trees should grow a little faster, grass should grow a little better, even crops should grow a little better, and that in turn means they'll be sucking up more CO2 from the atmosphere. So it's a negative feedback loop. But positive feedback loops exist too. So as the Arctic ice melts, The Arctic ice is white. It reflects sunlight back into space. Underneath it is water that's dark that absorbs more sunlight. And so that accelerates the rate of warming there. The feedback loops that we're really worried about are the huge amounts of carbon that are stored in the Earth or on the surface of the Earth that are not yet released into the atmosphere. So the oceans, the surface oceans have some, but the deep oceans have a huge amount, this 40,000 petagrams, so that's 40,000 billion tons of carbon. The plants and soil have a huge amount. Think about the Amazon, every swamp, every peat bog, every forest, and so on. So here's an example of one of these that is really dangerous. So in the far north, in Siberia, in Alaska, in northern Canada, we have permafrost. And in the permafrost is all sorts of vegetable matter that has been slowly decaying, but only very, very slowly because it's so cold, it's frozen. Well, as that area starts to melt and thaw, these things start to decay more rapidly, and they give off methane. Methane is natural gas, it's cow farts. It's also an incredibly potent greenhouse gas. Over 100 years, methane has 30 times the greenhouse effect of carbon dioxide, and most of that happens very, very quickly. So it's kind of an explosive feedback loop, if you will. This has happened before in history. The end of the last ice age saw the release of massive amounts of methane, and we can see in the climate record that the temperature soared by 15 degrees within basically one time slice of the data. So in maybe a decade, maybe 2 decades, the temperature changed enormously. Well, this is melting tundra and permafrost. This is what you call a thaw lake. A thaw lake is an area that used to be entirely frozen ground that is now melting and becoming lakes. And the water just kind of sits there because it can't actually seep into the ground below it because the ground below it is all frozen. But it's definitely a negative sign of warming. This is what used to be a home in Alaska that's just kind of washed away because the ground underneath it that was once frozen and solid has now turned into mud and allowed it to drift away. And this is a methane bubble. So this is a thaw lake. It's got a frozen surface, but within the lake and on the bottom, the sediment, this decay of material is happening, and it's giving off methane bubbles, and that's what you're looking at. This is a 45 centimeter bubble, so let's say it's like this. Okay? So, and this stuff is, as I said, it's natural gas. It's one of the most potent greenhouse gases we know of. And here's an example of somebody burning it. Someone just popped one of these thaw lakes and has set it on fire. So you can actually just set fires off of the Alaskan tundra right now. So if the warming doesn't get us, other effects of CO2 could get us. CO2 enters the water, seawater, and there it combines with water to form carbonic acid. And that makes the oceans a little bit more acidic. Not very much. There's carbonic acid in all of us, actually. Every time that you inhale and you hold your breath, some carbonic acid builds up in your blood. That's how we get the CO2 out of us. So a little bit's okay, but it's building up a substantial amount. And the problem with that is that two things that all life in the oceans depends on have problems with acidification. One is corals, which are sort of the rainforests of the ocean, if you will. About a quarter of the biodiversity of the different species in the oceans are nurtured in coral reefs. And the other are these plankton, the phytoplankton, that turn minerals in the water plus sunlight into other nutrients that other things can eat. They're the bottom of the food chain. That means everything that lives in the ocean eats off of something, that eats off of something, that ultimately eats off of these guys. And neither of these do well in acidifying water. And effectively, if we're at about 388 parts per million right now, what's to the left, it's still kind of a healthy system. If we get to about 500 parts per million, most analysis show the coral just dying. And in fact, the last time this happened was about 63 million years ago, as something called the Paleocene-Eocene thermal maximum, which is a thermal maximum means it's a time when the temperature reached the highest point, right? And it was an event that was actually about 10 times slower than what's happening right now in terms of carbon release. But it was still one of the fastest events in history. We're outpacing it tremendously. And if you go back to that era, you look at ocean sediments, Usually at the bottom of the ocean is sort of white and chalky as the shells of things that have died have kind of come to rest down there and made a white chalky sediment layer. Well, that white chalky stuff disappears entirely because there were no more things with shells in the ocean, at least not in the deep ocean. Nothing's getting down there. And if you look at archaeological sites around the world, or kind of not archaeological, but ancient sites around the world, millions of years old, you can find old coral reefs, the fossils of them in mountains, because the oceans used to be taller or higher back then. Well, all of those coral reefs were gone after this event as well. So the last time someone did something even a tenth as fast as what we're doing now, they killed off all the corals and killed off a lot of the life in the ocean. And that wouldn't be a great thing either. About a quarter of the world's protein comes from the ocean, or just even if we ignore the environmental impact of getting rid of these things. Okay, that's the climate stuff. Well, what about oil, energy? Well, so this is the world's most optimistic estimate about the future of oil. And this shows us peaking in total amount of oil produced in 2040. This is from the Energy Information Administration of the United States, which is probably a little bit more realistic. And it says we might be at the peak of oil right now. Basically, when you see unidentified projects, this gap between all the oil sources we know of and the blue line, which is what we believe world demand will be, unidentified projects means we don't know. We don't know how to fill this gap. All right? So that's not a great thing either. And in fact, we might be at the peak right now. So this is a graph of oil production over the last few decades. And it doesn't look that bad, right? It's just been going up and up and up since 1950. But it's kind of slowed, hasn't it? It's kind of tapered off. And there's that last few years, it's kind of looking flat there. Now, meanwhile, prices have spiked. They spiked once because of the oil crisis in the late 1970s, but they spiked again the last few years. And they spiked because demand, the amount of oil people want, is just exceeding supply. And in fact, if we look at the last almost 10 years, the last 7 years of oil production, it's been basically flat. Despite huge economic incentive to pump more oil, no one's able to. So let's just think about that. The oil price is this red line. The oil price is at a record high after decades, since World War II, of hanging out around 20 bucks a barrel. The oil price has spiked over 100 twice and kind of lingers there. So if you're an oil company, like, all right, we're going to pump more oil, make some serious money, but they're not able to. That blue line is how much oil they're actually pumping, and that's just not moving. And that's the scariest thing to me. I believe in the free market, I believe in capitalism, and I believe that faced with this incentive of the huge amount of money that they could be making by producing more oil, the fact that they're not able to says very negative things about the future of oil right now. And you can see it in other places. So that black line here is how much oil we've pumped, and the kind of grayish-green bars are new discoveries of oil fields. So you can see that for quite some time, since about 1980, we've been pumping more oil out than we've been discovering in new oil. There are all sorts of options for where to get additional sources of oil. One is tar sands. Tar sands are basically asphalt, actually. You can mine it up, stick it in a big chemical refiner, and produce oil out the other end. The problems with all of these, besides that we can't seem to do it quite fast enough, is that all of these things are much, much dirtier. So this is GHG here is greenhouse gas emissions. And you can see that crude oil has this much. When you go to tar sands, if you try to turn coal into oil, if you go to oil shale, all of them are emitting a lot more carbon dioxide per unit of oil that you're producing. So maybe you can get the oil out there, but you'll accelerate climate change at the same time, which is not necessarily a bargain that we want to make. Okay, so how are we doing here on time? So that's climate and energy. Let's talk about a few other issues, and we'll try to zip through these until we get to the possibility of solutions. Water. Most of the world's water is used for agriculture. People might tell you to take shorter showers or cook with less water, but really your water is mostly not this. It's mostly in the food that you eat. And the search for more water for agriculture has done tremendous things. Does anyone know what this is? This is the RLC. It's an in-water, or an inland freshwater lake, even though it has the name sea. It's between Kazakhstan and Uzbekistan. And the picture on the left is 1989, how big it was. Picture on the right is 2003. And here's what it's like today. So basically what happened was the Soviet Union, when it existed, wanted to irrigate its fields more. And so they pumped this lake dry, which was the 4th largest inland lake in the world. This is the Olagala Aquifer underneath the Midwest here, just a little bit south of here, a little west of here, I'd say. And these color codings are the rate at which the water table of this underground aquifer, this fossil water, this aquifer that's filled up over tens of thousands of years, how fast it's draining. Where you see red, the water level is dropping about 3 feet per year. So that's how fast we're pumping the water out of that. Food prices. I mentioned that in 2008, food prices spiked. They did, and they are continuing to again this year. So that kind of puts a dent in some of the good news we have. So if we sum all of this up, people try to put this together in a notion of kind of what's our ecological footprint. If we think about kind of the amount of nature it takes to produce our food, our water, to recycle, to capture the carbon dioxide that we emit and put it back into the earth, how much land does any one person take? How much land does civilization take? So the most recent numbers you see about this is that human civilization as a whole is using about 1.5 planet Earths. That's the number at the bottom. And that if all of humanity lived like we Americans live, we need about 5 planet Earths worth of services to offset what we do or provide what we do. And we don't have 5 planet Earths right now, so that's a problem. Okay, so the conclusion that many people come to from this is that our current prosperity is built on overconsumption, and that to end that overconsumption, growth must stop. That economic growth and the notion in our economies that growth is a key thing has to end. Bill McKibben, who's a wonderful man, who's a fervent environmentalist, wrote this book called Earth. The extra A there denotes that we don't live on the old Earth anymore. We live on a new Earth that we've changed. Paul Gilding wrote this book, The Great Disruption, how the climate crisis will put an end to shopping. Whoa, pardon me. Richard Heinberg, who's one of the people who's really thought about a lot about peak oil, wrote this book called Peak Everything, Preparing for the Century of Declines, telling us to just get, kiss goodbye to your current lifestyle because it's just going to get worse and worse and worse from here. Now, unfortunately, halting growth has a very real cost. One of those costs is that there is a high correlation between human well-being and prosperity. So this is a graph of energy consumption per capita on the right versus life expectancy on the top, or on the vertical axis there. And what you see is the countries that have high life expectancy use a lot of energy. And there are many graphs I could show you like this. But overall, if growth is ending, that's not good news for the few billion people who still don't have the wealth, the 5 billion people, we'd say, who live in the developing world still. What's more, if growth must end, then our world is zero-sum. Right? Zero-sum means for me to gain, you have to lose. Or for you to gain, someone else has to lose. Up until now, we've lived in a positive-sum world, where most countries have gotten richer together by cooperating. A zero-sum world has a lot of negative consequences. And you can kind of guess what they are by looking at some of these numbers. So around the world, the amount of trade that happens between countries is about 10 times the amount of money that countries spend on their militaries, right? We clearly put more energy, even the US and China, considered rivals, we put so much more energy into trading with China than we do into preparing militarily for a possible confrontation. And if the world is zero-sum, it's a very different situation than that. It's a situation where for you to grow richer, you can't do it in cooperation with someone else. You need to reach out and take it. And so now you think about things like the remaining oil supplies in the world. That starts to look like a very attractive target. Now, I would not be the first person to write a novel about warfare over oil supplies. I think Tom Clancy did that with his first novel, actually. Okay, so that's all the bad news and the worst news and why the worst news means even worse things, et cetera, et cetera. But I will give you some rays of hope. Predictions like this have been made before many times. So in 1968, Paul Ehrlich a respected biologist, wrote this book, The Population Bomb, where he warned, the first sentence in the book actually is, the war to feed humanity is over. At this late state, billions will die. There is nothing we can do to prevent a rise in the overall world death rate. Well, what happened was that the world death rate dropped and dropped and dropped, and the amount of food that we produce rose far faster than he thought that it possibly could have, and that the deaths from hunger have just dropped since then. The Limits to Growth came out in 1974. Best-selling environmental book of all times. It was kind of pioneering that they used a computer model to predict what would happen with the world. They plugged in to get very simple things like rates of consumption, rates of population growth, known resources, and they basically predicted that by 1992 the world would collapse. That ecological collapse would happen, energy collapse would happen, and so on. In 1992, I didn't notice the collapse if it happened. I might have slept through it or something. But Thomas Malthus, this is the original. So we talk about Malthusian. How many of you ever heard that term, Malthusian? So Malthusian means you're stuck. Your consumption is exceeding your resources. And it's named after this fellow, Thomas Malthus, who wrote an essay on the principle of population. And what he said was that population grows exponentially. It grows by a certain percentage each year. So maybe it grows by 10% each year. And that's compounding interest. So it grows faster and faster in real terms. Where food production can only grow arithmetically. It can only grow in a linear manner. And so therefore, population would always outstrip production, and you are destined for huge famine. And Malthus wrote this book just before the Industrial Revolution changed everything and ushered in kind of incredible wealth. And the population when he wrote this was less than 1 billion, as opposed to 7 billion today, who live in greater health and with more food than when he wrote this. So all of these were wrong, and they were all wrong in the same way. They were all missing one key ingredient, which is innovation, which is the ability to produce new ideas that increase the value of resources around us. So growth and useful knowledge, that's how I define it here. So knowledge is the ultimate resource. It is infinitely reusable. If I give you an idea and you use it, it doesn't get worn out. You don't have to replace the parts on it or anything like that. It grows over time. It's the only natural resource we know of where our stockpiles now are bigger than last year and far bigger than they were 20 years ago, for instance. It's non-rival. So this is sort of the sharing aspect. Economists talk about rival goods are, let's say, this bottle of water. Only one of us can have it. That's a rival good. A non-rival good is like an idea, or to some extent, the air that we breathe. It's something that we can all benefit from at the same time, maybe up to certain limits. And it is a multiplier. It multiplies the value of everything, of labor, of energy, of land, of materials. So let's talk about a concrete example of this, food production. As I said, this is the first energy technology we ever devised, produced energy for our bodies, and it's the most important. Without this, we can't have a functioning society. So when Paul Ehrlich wrote his book, 1968, we were right about here. My red light has gone out. And what happened is something called the Green Revolution happened. And the Green Revolution wasn't about environmentalism directly. It was about producing more food. And it was better varieties of seeds, better use of fertilizer, better use of water. And it has nearly tripled the worldwide yield of food per acre. Now, some people say we're eating oil, that this is because of the energy we stick into the food. So first, it's not. Like if you look at the energy output of crops, it's usually at least 10 to 20 times the energy that we put in. But more importantly, it's a much longer term trend. So this is the trend in food people fed by 1 square mile of land over the last 12,000 years. And it's on an exponential scale, a log scale on the right-hand side here. So it goes from about half a person fed by 1 square mile of land in hunter-gatherer times up to multiple thousand fed by 1 square mile of land today. Or you can think of it the other way in terms of our ecological footprint. How much land does each of us take up in terms of the land needed to feed us? And that's gone from 10 square kilometers down to about 1,200 square meters. So it's dropped by a factor of almost 10,000. So So this is a graphical depiction of this. This is the amount of land it takes from Google Maps to feed one hunter-gatherer. And then this is the first farmers. This is a square in the upper left there. And then different civilizations have kept innovating in farming and kept shrinking the amount of land it takes to feed one person. So that's the power of innovation. The amount of sunlight falling on this land hasn't increased, and food basically is turning sunlight into calories for us. It's that we've gotten smarter. We've gotten better ideas that multiply the value of the land, multiply the amount of the energy that falls onto it that we can capture. So this is the environmental impact of that in the US. This dotted line is how much farmland we would have needed to have to feed our current population with old yields, with the yields we had at the start of the 20th century. And what you see is it would have taken all the land east of the Mississippi added on to our current agricultural land. In effect, it would have chopped down all forests in North America to provide food just for Americans. And if you look at this on a global scale, if we had not raised food yields, either we would have had that mass starvation and billions would have died, or we would have had to have turned every bit of forest on the planet into farmland to meet our needs, which we didn't have to do, fortunately. Okay. So this is more stuff. This is the amount of energy that goes into farmland in the US. And this is a better way to look at this. This is the energy use per calorie out. So how much energy do we have to use in fertilizer, in running farm equipment, and so on to produce 1 calorie of food? And that's dropped by about a factor of 2 over the last half century or so. This is, I told you that the the energy in is smaller than the energy out. The black bar here is energy that we put into farming in terms of running machinery, fertilizer, and all those other things. And the white is energy that we get out of these crops for that amount of space. And we've done this by increasing efficiencies in lots of ways. We use a lot of fertilizer these days, but we've been able to do that because we've dramatically dropped the amount of energy that it takes to produce a unit of fertilizer by a factor of more than 5 over the last century. Even today, this is wheat output per unit water. We are more efficient in growing food, not just per unit land, but per unit water that we put in. This is another one like that. This is not just true in food production. This increase in efficiency or this multiplication of natural resources is true everywhere. This is sort of a famous graph saying how many hours of work does the average worker have to do to get 1,000 lumen hours of lighting? And you see that it kind of dropped steadily for thousands of years. Then during the Industrial Revolution, it plummeted as we got better technology, and it's kept dropping until now. And part of that is the efficiency with which we can create light. Using a candle is about 0.3 lumen hours per watt of energy. Using a white LED is about 150 lumen hours per unit of energy. So we've increased the efficiency with which we turn energy into light by a factor of almost 500. This is the energy it takes to run an average refrigerator. It's dropped by about a factor of 4 since the late 1960s, largely due to the Energy Star program that mandated this. But it clearly, those efficiencies were there if we innovated in the technology to realize them. The steam engine, everywhere we look, we've increased efficiencies. And that means we've actually entered an era where in some cases we're using less on a per capita basis than we used to. This is the amount of oil that the average American uses per year. And what you see is that it peaked in about 1970 and it's actually down by about a third since then. And this is true in Canada, it's true in Europe as well. Energy consumption per person is about flat. It's actually a little bit lower than it once was in the US. Water production has fallen off by more than a third in the US per capita as farming has gotten more efficient. If you look at this in terms of how much economic value is there per resource, this is the ratio of amount of water per dollar of GDP in your economy. And you see it's just plummeted over time. Even the carbon that we emit a little bit less carbon dioxide as Americans per capita per year than we used to just a few decades ago. And if you look at the projections here for the future, The projections that we have are that the amount of energy that we will use as Americans per person will drop slowly over the next few decades as well. They'll continue that decline. But another way to look at this is how much energy do we use per unit of our economy, right? And that has dropped substantially already by almost half in the last few decades and is on track to keep dropping. So a lot of the wealth that we're creating now comes not from using more resources, but using those resources more intelligently to produce more value. Let's keep going here. Okay. So this is an interesting concept related to that, which is in pollution. There's a hypothesis that I'll say is quite controversial, but it's worth knowing about and thinking about, because it applies in some places, and it's called the environmental Kuznets curve. And one of the prime studies of this is how much of a pollutant does an economy produce. So this is the amount of sulfur that economies produce per person related to how rich they are. So this is gross national product per capita, rich countries over here, poor countries over here, and the y-axis is how much of this pollutant do they produce. What we see is that very poor countries have no industry, so they don't produce this pollutant at all. And then it's the countries that are starting to get rich and are going through the first phases of industrialization, where they're using very dirty technologies that are producing a lot of the pollutant. And then as countries get richer than that, something happens, which is that people inside those countries start to care about the quality of their environment. And so they push for changes. They push for cleaner businesses, they push for regulation, and that ends up dropping the amount of a pollutant that is produced. That's this model over here. So this, to me, this links to another thing, which is that in general, the richer a country is, the more efficiently it will produce something. So a richer country will use more of a resource. Even though oil consumption in the US is dropping per capita, we still use far more oil per capita than does someone in a poorer country. But we tend to get more value on a per unit basis out of the resources that we use. So I'll give you an example here. This is the amount of rice you can produce for a given amount of water. And it's hard to read this, and I apologize. What you'll see is that on the very far left is Vietnam, Iraq, Cambodia, poor countries. And on the very right, at about 3 times that level, you have the United States of America. So we are actually the most efficient farmers on the planet in many crops, we and Europe and Canada and Australia, in terms of the amount of energy it takes per unit output and in terms of the amount of water that it takes per unit output. And the reasons for that are really clear. If you're in Vietnam, you can't afford an irrigation system. So the way that you irrigate your fields is you flood the field. And that takes a lot of water. In the US, increasingly you see things like drip irrigation, where the total amount of water that's placed on the ground is relatively small and very targeted on just what you want to, just where you want it to go, just where you want it to have an impact. This is for a variety of crops. How much water do different nations use? So the US is the top bar in all of these. And what you see is compare the US to, say, India, and you look at how much water we use to produce a ton of corn here. And you have India using almost 4 times what the US uses. We have nearly 2 times what the US uses to produce wheat. And again, that's because we've developed and employed better technologies inside the US. And this is true not just for water, it's true for land as well. I showed you that increasing farm productivity, but it's not even all around the world. In the richer countries, you have higher productivity per unit land. So again, you'll see North America and the EU have incredibly high yields of all grains per unit land, whereas Africa and South Asia, India and Pakistan, have very low yields. So in a certain way, while the rich consume more, the rich are also more efficient. And what we'd like to see is actually to spread some of the more efficient technologies that we have to other parts of the world so that they can get the benefits of higher yields with lower impacts. Okay, so we know population will plateau. The current projections show that population will max out at somewhere just under 10 billion people. Even as we've just hit the 7 billionth person on Earth, the rate at which the population is growing is ever slower each year. We haven't added as many people in the last year as we did in the late 1980s, for instance. And that shows us eventually plateauing and possibly even declining. So if population plateaus and declines, and we can get to the point where per person consumption of a resource plateaus and declines, then we'll eventually get to a point where overall consumption declines, okay? And if we look at this Kuznets curve model of high use when you're at kind of medium wealth and eventually getting to less use of a resource or less pollution when you're rich, what we want to know is, are there shortcuts? Can we skip that worst part of the curve where we're least efficient or polluting the most and get to the other side? It's possible. This is a big question. I'll say that it is happening in other countries. So when we look at the amount of carbon released per dollar of wealth in a country, this is a long-term graph of the US, Japan, and China. And what you see is that China has dropped their amount of carbon emitted per dollar of production dramatically. They're still putting out twice as much carbon per dollar as the US is, but that's nothing compared to the ratios that we were looking at of 5 times, 6 times back in 1980. So what's happening here is sort of a Kuznets shortcut, if you will, that China, and along with China, India, and other countries, are being able to adopt some of the newer technologies developed in the US and Europe and Japan and put them to use in their economy. And that's happening because knowledge is non-rival, because an idea can spread easily from place to place. And so this is good news for the world. And if anything, we just want to accelerate that process. So what are the limits? How far could we go, and how rich could we be while protecting the planet? Well, to me, it starts with energy. We've talked about food, water, and so on, but energy is now the heart of it. With sufficient energy, you can solve a lot of problems. Without it, you have a lot of new problems. The ultimate source of energy that we know of is the sun. How much energy? A tremendous amount. So this large yellow circle on the left is the amount of energy the sun provides the Earth in a given year. This small pie chart on the right is all known reserves of all fossil fuels. Not just 1 year's worth, all that we know of on the planet. So that's an incredibly larger source overall. So the planet uses 15 terawatts of power, and the sun strikes us with nearly 90,000 terawatts of power. What that means is that 14 seconds of solar energy striking the Earth, about as long as it takes me to say this sentence, is enough energy to power all of humanity for 1 day, if we could capture all of it. 88 minutes of insolation, less than the amount of time that we'll spend in this room, is enough energy, just the amount striking the Earth, to power human civilization for 1 year. So the size of the source is enormous. And this, imagine, if you will, that there's a map of the Earth here. These little dots are the amount of space, these little blue squares are the amount of space it would take with current efficiency solar cells to capture as much energy from the sun as all of humanity uses today. It's about 500,000 square kilometers, which sounds like a lot, but on Earth there's 150 million square kilometers of dry land and about 500 million square kilometers of surface area total. So that's 1/3% of the Earth's land surface area is all that it would take to capture enough energy from the sun to replace all the energy sources that we know of right now. And that's about 1% of what we use for agriculture, and it's about 3% of the size of the world's deserts. The problem with solar energy has been cost. We can capture it, but if it costs a huge amount to make each solar panel, it doesn't matter that the energy is abundant. It just doesn't make any sense to go ahead and do it. But solar, like other technologies, like computer technologies or cell phones or televisions, has been dropping tremendously in price. So the first solar cell was developed in 1954, and it cost $1,000 per watt of electricity that it delivered. Today, at the end of 2011, the prices are about $1.20 per watt of energy captured for a solar panel. So it's dropped by about a factor of 1,000 in that time. And it seems to be dropping in half roughly every decade. And what that means is that we're on the verge in just the next few years of getting to the point where solar photovoltaic cells, if this trend continues, will be cheaper in the electricity that they generate than coal plants or natural gas plants, which is how we get most of our electricity today. So there was just an announcement a few months ago. General Electric said that they believe that by 2015 they'll have solar electricity in California that is market competitive. And another company, First Solar, a solar company, said the same thing, and they said 2014 to 2016. So we're just about to cross this threshold point. And you see it here in this couple-year-old graph showing that around 2015 is when we're in the middle of this price area. But it all depends on this incredible price decline that we've seen over time. And that price decline is just pure innovation. The way that we've done it is we've made cells more efficient. They've learned to make cells thinner. They've learned to make cells out of things other than silicon. So all of those kind of new scientific discoveries and new innovations are what's powering this potential here. Now, capturing that energy is good and well, but there is this thing called nighttime, and there are these things called cloudy days, when the sun is not an effective source of energy, particularly nights. And so it's important to us to capture that energy or provide some other way to provide electricity at night when you're at home watching your television, or so things can charge and operate at night. And a lot of people have pointed this as a reason why solar will never fully take off. But even that seems to be something where we have this exponential trend happening. So this is a chart of the energy cost of lithium-ion batteries. Lithium-ion batteries are the batteries you find in your cell phone and your laptop. They're everywhere. They're ubiquitous. And what's happened is that in 1991, they cost about $3 per watt-hour stored. And today, they cost about 30 cents per watt-hour stored. And at the same time, the blue line here is energy stored per unit mass. So that's gone up. That's about doubled in that time. So now a 1 ounce battery stores about twice as much energy today as it did in 1990. But more importantly for the solar grid is it costs about 1/10 of what it did for that energy storage. And so again, if this trend continues, which is all about innovation, then we'll have the ability to both capture that incredibly large source of energy and store it for use overnight and on cloudy days. And at that point, we really could talk about eventually phasing out fossil energy sources of power. And in fact, I'll give you one stat on this right now. In 2004, 98% of the power of the electrical capacity added to the US grid, so the new plants built and so on, was fossil fuels, was coal plants and natural gas plants. In 2009, which is the last year that we have really good data on this for, that was only 45%. And 55% of what was added was renewables, wind and solar. Wind primarily, solar, and a little bit of hydro. So that shift is happening right now towards using more and more green energy sources, if you will. Another way to capture solar energy is to turn it into a fuel. So why fuels? Well, the big thing with fuels is energy density, right? So we talk about watt hours or kilowatt hours. On your electric bill at home, you get charged for kilowatt hours. A kilowatt hour is 1,000 watts, which is power, the rate of energy used for 1 hour. Well, a gallon of gas, or a kilo of gas, 2 pounds of gas, about a quarter gallon, stores about 30 kilowatt hours of energy. To get the same amount of energy, you would need about 10 times that weight in batteries. So that's why when a friend has an electric vehicle, or you hear about them, they don't go very far, because the batteries just don't store nearly as much energy as a fuel does. So that's the big advantage that fuels have today. Plus, to go to solar power for our transportation, we would need to actually replace all the vehicles that are out there that burn gasoline or diesel today with electric-powered vehicles. And that's a multi-trillion-dollar investment. You know, when you have more than 1 billion vehicles on the road around the world today, we're looking at 2 billion vehicles by the end of this decade that are all geared to burn gasoline or diesel. Replacing them would be a very expensive proposition. So we'd love it if we could find some way to power those vehicles with a fuel that doesn't come from digging up old carbon from the ground and releasing it into the air. So fuels are a possibility of this. And the basic idea of all solar fuels is that energy in plus carbon dioxide, usually plus water, produces a fuel. All right? This is Craig Venter. How many of you know who Craig Venter is? No one knows who Craig Venter is. Craig Venter is a future Nobel Prize winner, I will say. So this is the man who led one of the 2 different approaches to sequencing the human genome. And he was in private industry, and his team came in with an entirely new technology based on computers and sequenced the human genome dramatically faster than the government-funded approaches did. And he's talking about designer fuels here. The reason he's talking about it is that his current venture is one where a partnership between his company and ExxonMobil, where they put $600 million together to create new designer organisms. They're doing bioengineering, genetic engineering to create a variant of algae that turns sunlight plus water plus carbon dioxide directly into a fuel you can stick in your gas tank. Now, will he succeed? I don't know, but he's one of about 120 different companies that are working on this right now, and the basic biology, physics, and chemistry say it's possible. In large part, if it's going to happen with fuels, it's going to happen because of genetic technologies, because we've gotten a lot better at reading genomes, deciphering them, and editing them. So you probably know about Moore's Law. How many of you have heard of Moore's Law? So Moore's Law is very roughly that computers get a lot faster and get a lot cheaper over time, right? It's that the number of transistors you can put on a chip drops or increases by about 40% per year. So it doubles every 2 years. But we may take that to more or less mean that the amount of computing you can buy for $1 doubles every 2 years, more or less. So the lighter blue line here is the rate of Moore's Law. The darker line is the rate of DNA sequencing. So how many DNA letters can you read for the same amount of money? And that's going even faster than Moore's Law. So of all the places we can measure a rate of innovation and quantify it as X% better per year, this is probably the single fastest one on the planet we could find today. And what that means is that all of the few thousand genes that exist in algae and exist in other single-celled organisms that are potentials for generating fuel, these folks have now sequenced and resequenced and resequenced and are trying to decipher exactly what the purpose is and to build designer organisms that spit out fuels. Old biofuels had this phenomenon where the algae or the other nutrient that you used, or the other organism that you used, would build up sugars inside of itself. Then you had to go ferment that sugar, basically. You know, all the alcohol you buy is fermented sugars. So they would go ferment this sugar and produce ethanol out the other end. The new generation of biofuels, what they're calling second generation biofuels, will be genetically engineered organisms that are just designed to either produce ethanol or produce diesel or produce even gasoline as just a normal process of their metabolism. So you won't have to take these animals, harvest them, grind them up and process them. You just have a little spigot on the tank in which the algae is growing, and you turn it and fuel comes out, essentially is the model here. This is an artist's conception of a biofuel facility. One of the nice things about algae and many of the other organisms people are looking at for biofuels is they can grow on salty water, they can grow on wastewater. So there are a number of problems with current biofuels. So biofuels today really means corn or sugarcane, and those are limited in their utility really by a couple things. One is the yield you get out of them is very, very low. So the number of acres you would need to replace the current use of oil in America with corn ethanol is larger than all of America. So the yield is low. Another is they compete with food crops. So when we look at the price rises that have happened in basic foods over the last 3 years, a chunk of that has been that a third of the US corn crop now goes to corn ethanol. And that is really, it's a waste because it's not very efficient, and it's also something where we don't really want our energy needs to be competing with our food needs. We'd like to find unique, different resources to tap into. So with most biofuels we look at now, they are biofuels that can grow in deserts, on salt water pumped in from the shore. And the potential yields are huge. It's easy to look at a graph like this and think, well, I'm just going to take that with a grain of salt. And we should. But a number of companies now are claiming that in the next couple years, they will have biofuels on the market in large scale cheaper than existing gasoline. And in fact, DARPA, this is the Defense Advanced Research Project Agency, the successor to the agency that created the internet, among other things, they have a congressional mandate to make sure that the Air Force and Navy can operate aviation on biofuels and to find alternate ways to produce fuels. One of the reasons for this is energy security. We don't want our foreign countries cutting us off. Another is the incredibly high cost of fuel in war zones. So there's a quote out there that in Afghanistan, the average cost per gallon of gasoline is $174. And what that is that's the cost of the convoys and the troops around those convoys that are trying to make sure that the fuel gets there. So DARPA's vision is, instead of trucking the fuel in, you would actually build a biofuel plant in your forward war zone, and you would generate the fuel that you need right there. So they're funding a lot of projects in this area. And someone from DARPA claimed last year that they see $5 per gallon algae-based biofuel on the market in 2014. So that today I think gas is under that, but that's close enough. That's starting to look very attractive. And unlike oil, where we're having to pump more wells deeper and farther and dig more dry wells to get at this finite amount, the sun will keep shining for another few billion years. So the energy source is effectively unlimited if we can learn to turn solar energy into energy that we can effectively use. There are also ways in theory to do this without biology. There are chemical ways to capture CO2 and turn that into fuel, and that's something that's being actively investigated at a variety of places too. And now it's easy to miss this, but a key benefit of this is that when you're looking at biofuels or any fuel where the carbon came from the air, it's carbon neutral. What that means is that when you burn a biofuel, you're still pumping CO2 back into the atmosphere. The difference is that the CO2 you're pumping into the atmosphere was extracted from the atmosphere to make the fuel that you're burning. And so it's not adding any net new CO2 to the atmosphere, and therefore it's not exacerbating climate change. Okay, so if we can crack energy, we can crack almost everything else. Water is one of those things. We access less than 0.1% of the water in the world. We live on a water planet, so it's ridiculous we should have any water shortages at all. But most of that water is salty. So the question is, can you convert that salty water into non-salty water? Well, it used to be that the way that we did that was we boiled the water. So very easy way to desalinate. You boil the water, collect the steam in another chamber, and it's fresh water. In fact, Benjamin Franklin, he was Secretary of State, issued a memorandum to all parts of the US fleet describing how to make a freshwater distiller, and that this sign be placed on every boat so that should they have a problem, they would know how to make fresh water for themselves. Nowadays, they make fresh water from salt via semi-permeable membranes. So they take basically plastics. They've learned that human cells are semi-permeable. They can let some things in and leave some things out. So inspired by this, they've designed plastics that you can push water through, and the salt stays on one side, but the fresh water keeps on through. And that has cut the amount of energy it takes to desalinate water by a factor of 10 since 1970 as well. And that's the upper left of this graph. That's the amount of energy it takes in these bars to desalinate water. Has gone from about 15 kilowatt hours for a cubic meter of water, so like 250 gallons, down to about 1.5. And that means that we have plentiful energy on this planet to desalinate more than enough water for everyone, if we can get that energy in a sustainable way. Food yields. This is one of the most solvable problems that's impeded today, even not by technology, but by development and politics. So we already know that in the US and Europe and Canada, we have food yields per acre that are twice that of the world average. The problem is that in sub-Saharan Africa and in South India, they're not using the intensive methods that we have. They don't have mechanization, they don't have drip agriculture, they don't necessarily have the seeds that we have. So if all we did was not even to innovate, but to simply find ways politically and economically to help people in those areas invest in more intensive agriculture, we would double the planet's food output. And that would more than meet our needs through 2060, 2070, something like that. Beyond that, we can innovate. So we've raised food yields for decades now. Since 1960, they've about tripled in the US. And there's further opportunities. This is just one example. It's one of my favorites. Photosynthesis is the process via which cells convert sunlight and water into sugars and then into fats and other nutrients inside of themselves. And there are different photosynthetic pathways in different sorts of plants out there. So most plants that we grow use something called the C3 pathway that has a maximum efficiency of about 4.6%. 4.6% of the sunlight can be turned into energy that could be treated as food. There's something called the C4 pathway, which sugarcane uses, that has about a third better, for instance. So there's now a project to find a way to genetically engineer rice so that it becomes a C4 crop and grows in its yield by about a third. And this is just one project out of literally dozens of different ways that we could continue to innovate on the crops themselves to produce more food. So the potential's out there if we innovate. And in fact, this is now the amount of land it takes to feed one person on Earth using the current best farming in the US or Europe. And if we got to the maximum efficiency that photosynthesis can ever run at, which is 13%, that's how much land it would take, about 1/40th as much. So the actual limit on how much food we could produce on Earth, just going by the physics of it, is incredibly, incredibly high if we can keep innovating to get there and if we can solve the economic and political issues to spread the technology out widely. Okay, so all of this growth is possible, but as I said, possible doesn't mean that it's going to happen. Some things are not looking as good as we'd like. The energy has been decarbonizing for a long time, meaning the amount of carbon released per unit of energy used has been dropping, but the rate at which it's been dropping has been slowing. So it was dropping at 2% per year in the early 1990s, and now it's dropping by about 1% per year. So that's the wrong direction. We'd like it to be finishing up quickly and get to a point where we have basically a zero carbon economy. There are challenges that are in our way. The first challenge is just scale. I showed you this chart before. Again, imagine a great map of the planet here. That's the American Southwest is the upper left there. Even though this is only 1/3 of 1% of Earth's land area, that is enormous. It's still 500,000 square kilometers. So it's one of these numbers that is simultaneously very small compared to the potential, compared to how much land we have available, and very large compared to the size of the project. And even with the dropping cost of solar, this will be a multi-decade and tens of trillions of dollars size project. Now, that investment will pay itself off easily. It'll pay itself off by cheaper energy that'll fuel economic growth and fuel building buildings and building vehicles and all the things we want to do. Powering our data centers, we can play farmland, Farmville, I suppose. But it's still an epic size project that we have to engage in. The other challenge, and this is what I think is the big challenge, is a bug in our software. So I'm a computer scientist by training. I think about algorithms and software and how it works. And I will tell you that the software that runs human civilization is capitalism. Governments are so big, the market is 3 times larger than all the world's governments put together. So the basic notion of self-interest and transactions of money for goods and services is what runs the planet, and it's been tremendously successful. Everywhere that we look where capitalism has come in to succeed previous systems, it's raised wealth tremendously. Just looking at these numbers, when China opened itself up in 1978, its rate of growth nearly tripled over the previous few decades. China went from having 270 million people in poverty in 1978 to having 70 million in poverty in 1985, just 7 years later. Similar things happened in India after 1991, when India opened itself up to the world. That India was effectively broke. You talk about the credit crisis in Europe and so on now. India was in a situation where no one would even loan money to India because they thought the country was that bad of a risk. And so in '91, faced with this, they made huge changes and went to a less socialist and more capitalist economy, and it did wonders for them.